Linear Algebra II, Lecture 10, Gram-Schmidt process. Let's recall what we did on the previous lecture. Let E be an Euclidean space. An Euclidean space consists of a vector space, let's call it V, and a fixed inner product on V. An inner product is a symmetric, bilinear, and positive definite form. So we have two arguments from V, and the output of the form is a real number, and this form should be symmetric, bilinear, and positive definite. So we discussed that in each Euclidean space we can define natural geometric notions. The notion of a length of the vector, also known as a norm of the vector. So the length of the vector V is defined as a square root of the inner product of V with itself. And we can define the angle between two vectors. So if we have two vectors, both non-zero, then the cos of the angle between these two vectors is defined as the inner product of them divided by the product of their lengths. And we have seen last time that this gives a real number between -1 and 1, so we can treat it as a cos of some angle, and so we can define an angle between two vectors. And two vectors are called orthogonal if the scalar product between these two vectors is 0. So in particular, the 0 vector is orthogonal to any other vector in the space. And we also defined the notion of an orthonormal basis. A basis of an Euclidean space is called orthonormal, provided that all vectors in this basis have length 1, and they are pairwise orthogonal. We introduced this notion, and the main point today is to prove that such bases exist. So we know that all finite dimensional spaces have some bases, but now we specified some properties, so we need to prove that bases with such properties exist. Okay, so the main result of today's lecture is the following theorem. Every finite dimensional Euclidean space has an orthonormal basis. And this theorem follows directly from the following proposition. Let V1, V2, and so on Vk be a collection of linearly independent vectors in E. Then there exists a collection W1, W2, and so on Wk of vectors in E such that these vectors are orthonormal, so they all have lengths 1, and they are pairwise orthogonal, and such that the linear span of the vectors v1, v2, and so on vk is equal to the linear span of the vectors w1, w2, and so on wk. And then this proposition immediately implies our main theorem. Indeed, we can take any basis in our Euclidean space. We know that such basis exists, we proved that. And now applying proposition produces an orthonormal basis in our Euclidean space. So let us prove the proposition. In order to prove the proposition, we will do induction on K, on the number of vectors. So we proceed by induction on K. The basis of the induction is the case K is equal to 1. Note that by the assumption the vector v1 is supposed to be linearly independent. In particular, it must be non-zero. So it has non-zero lengths. So let us define the vector w1 to be v1 divided by the length of v1. Then the linear spans of these two vectors, v1 and w1, they clearly coincide because these are two non-zero vectors which differ by a multiplication with a non-zero scalar. So let us check that w1 has length 1. We only have one vector, it doesn't have to be orthogonal to anything, so the only condition to check is that it has length 1. So the length of w1 is equal to the length of v1 divided by the length of v1. So 1 divided by the length of v1 is a positive real number, so we can take it out of the length sign, and so we get the length of v1 divided by the length of v1, and this is equal to 1. So w1 has length 1. In particular, it's non-zero because it has non-zero lengths. So w1 is a normed vector, and the linear span of w1 equals the linear span of v1. So this completes the proof of the basis step of the induction. Now let us prove the induction step. Let us forget the vector vk. Then, using the induction step, there exist vectors w1 and so on wk minus 1, such that they all have lengths 1 and are pairwise orthogonal, and such that the linear span of v1 and so on vk minus 1 equals to the linear span of w1 and so on wk minus 1. Define the vector wk tilde as follows. So we take the vector vk, and then we subtract the linear combination of these wi's, where I is from 1 to k minus 1, and the coefficient at wi is the scalar product between vk and wi. So this defines the vector wk tilde. Now let us check that this vector is orthogonal to all vectors w1 and so on wk minus 1. So let j be a number between 1 and k minus 1. Let us compute the scalar product between wk tilde and wj. We can insert, instead of wk tilde, its definition, so it's vk minus the sum of wi's with coefficients vk, wi, and then we take the scalar product with wj. Using the bilinearity of the scalar product, we can rewrite this as the scalar product between vk and wj minus the sum over all I from 1 to k minus 1. Then we have this coefficient, the scalar product of vk and wi, and finally times the scalar product between wi and wj. Since wi and wj belong to an orthonormal system of vectors, the scalar product is 0 unless I is equal to j. So in all this sum, there is only one non-zero summand, and this corresponds to I being equal to j. In that case, wi and wj, their scalar product is 1, so this factor just disappears, and we are left with vk scalar product with wj. So this summand and this summand, they cancel, and we get 0. This proves that the vector wk tilde is orthogonal to all the vectors w1, w2, and so on wk minus 1. Next, let us note that the vector wk tilde is non-zero, and this is because the vectors v1 and so on vk are linearly independent. The vector wk tilde is a linear combination of those vectors. So here we have vk, and here we have a linear combination of wi's, but their linear span is equal to the linear span of v1 and so on vk minus 1. So the summand here is a linear combination of v1 and so on vk minus 1. Therefore, since v1 and so on vk minus 1 and vk are linearly independent by assumption, it follows that wk tilde is non-zero. And so we can define wk as wk tilde divided by the lengths of wk tilde. And the same computation as we did for the basis of the induction shows that wk has lengths 1. And of course, this wk is orthogonal to all other vectors wj, where j is smaller than k, as in the previous slide. So we can compute this. So wk is wk tilde divided by the length of wk tilde. We can use bilinearity to move the scalar out of the inner product, and then we have the inner product of wk tilde and wj, and we know that this is 0. This was computed on the previous slide. So this means that vectors w1, w2, and so on wk are all normed and are pairwise orthogonal. So the final thing, we need to prove that the linear span of v1 and so on vk is equal to the linear span of w1 and so on wk. If you look at the definition of wk tilde, the vector vk is equal to wk tilde plus the linear combination of wi's. In other words, vk belongs to the linear combination of wk, the coefficient will be the length of wk tilde, and the vectors w1 and so on wk minus 1. And since the linear span of W1 and so on Wk minus 1 equals the linear span of V1 and so on Vk minus 1, we obtain that the linear span of V1 and so on Vk equals the linear span of W1 and so on Wk. And this completes the proof of our proposition. And the method, how you construct an orthonormal basis, starting from a linearly independent sequence of vectors, as outlined in this proposition, this is usually called the Gram-Schmidt process. Here is an example. Let us construct an orthonormal basis in the following subspace of R4. So we consider the Euclidean room E4, so this is R4, with respect to the standard inner product. And we consider the subspace of V, which is generated by the vectors 1, 0, 1, 0, 1, 1, 1, 1, 2, 1, 2, 1. So let us try to construct an orthonormal basis in this subspace. We want to apply the Gram-Schmidt process described by the previous proposition, but in order to be able to apply it, we need to start from a linearly independent set of vectors. So here we have V generated by 3 vectors. Let's find some basis in V. So let's find out which of these vectors are linearly independent. So in order to construct some basis in V, we write the generating vectors as columns in the matrix, and we need to reduce this matrix to a row echelon form using Gauss elimination. So here we readily see that row 1 and row 3 are the same, so we can delete row 3. Row 2 and row 4 are the same, so we can delete row 4, and we immediately get a matrix which is close enough to the row echelon form. So the first row is 1, 1, 2, and the second row is 0, 1, 1. So we have 2 leading elements, one in column 1 and the second leading element in column 2. So this means that the first 2 vectors in our set, the first 2 columns, form a basis in V. So V has dimension 2, and the basis is formed by the first 2 vectors which generated. The third vector is redundant. So we take these vectors, let's call them V1 and V2. So V1 is 1, 0, 1, 0, and V2 is 1, 1, 1, 1. And let's apply the Gram-Schmidt process. The vector W1 is by definition V1 divided by the length of V1. So V1 is 1, 0, 1, 0. So its length is the square root of 1 times 1 plus 0 times 0 plus 1 times 1 plus 0 times 0. So its length is the square root of 2. So we will get the vector 1 divided by the square root of 2 times 1, 0, 1, 0. The next step of the process, we construct the vector W2 tilde. By definition, this is equal to V2 minus the vector W1, which we have here, with the coefficient, the scalar product between V2 and W1. Since we know that W1 is 1 divided by the length of V1 times V1, we can rewrite this as follows. So the first summand is V2 and then minus, and then we have the scalar, which is the scalar product between V2 and V1, divided by the scalar product of V1 and V1 times V1. So we just plug in the definition of W1 in this formula and use bilinearity of the scalar product. Now let's compute. The vector V2 is 1, 1, 1, 1. The vector V1 is 1, 0, 1, 0. The scalar product between these 2 vectors is 1 plus 0 plus 1 plus 0, so it's 2. And the scalar product of V1 with itself, we computed here, so it's also 2. So this means that W2 tilde is 1, 1, 1, 1 minus 1, 0, 1, 0, which is 0, 1, 0, 1. And now we can compute W2 as W2 tilde divided by its length. So the W2 tilde is the vector 0, 1, 0, 1, and its length is the square root of 0 square plus 1 square plus 0 square plus 1 square, which is the square root of 2. So W2 is a vector 1 divided by the square root of 2 times 0, 1, 0, 1. And the answer is that the vectors W1 this is this vector, and the vector W2, this is this vector. These two vectors form an orthonormal basis in V. Here is the second example, more complicated. Let us consider the set of all polynomials with real coefficients of degree at most 2. Let's consider the space as an Euclidean space with respect to the inner product given by the following formula. The inner product between the two polynomials f of x and g of x is the integral between 0 and 2 of f of x times g of x dx. So we have shown that this kind of formulas always define an inner product on the space of polynomials. Let us determine some orthonormal bases in this Euclidean space. So we need to apply the Gram-Schmidt method to some bases of the space, and there is a standard basis in any polynomial space which consists just of the powers of the variable. So we have polynomials of degree at most 2, so the standard basis consists of the polynomials 1, x, and x squared. So now let's do the Gram-Schmidt orthogonalization for this set of vectors. And so this is a basis, in particular the vectors in the set are linearly independent. So f1 of x, by definition, is equal to the element 1 divided by its length. And the length is with respect to this inner product. So let's compute the length. So the length of 1, of the polynomial 1, is by definition the square root of the integral from 0 to 2, 1 squared dx. This is the integral of 1 between 0 and 2, so the answer is 2. So the length of the polynomial 1 with respect to this inner product is the square root of 2, which means that the first basis element f1 is equal to 1 divided by the square root of 2. So this is a constant polynomial for this constant. For the next step, we need to compute f2 tilde, and this is by definition x, our next element, minus the inner product between x and f1x times f1x. Similarly to the previous example, we can rewrite it as x minus the inner product between x and 1 divided by the inner product between 1 and 1 times 1. So we need to compute the inner product between x and 1. So this inner product is the integral between 0 and 2 of 1 times x dx, and this is just the evaluation of the function x squared divided by 2 at x being equal to 2. So this is equal to 2. So the formula for f2 tilde gives us x minus 1, because it's x minus, here we have 2, here we have 2, 2 divided by 2 is 1. So f2 tilde is equal to x minus 1. Therefore, f2 is equal to 1 divided by the length of x minus 1 times x minus 1. Let's compute the length of x minus 1. The length of x minus 1 is a square root of the integral from 0 to 2, x minus 1 squared dx. So x minus 1 squared is x squared minus 2x plus 1. And so this integral is equal to the evaluation at x is equal to 2 of the function x cubed divided by 3 minus x squared plus x. And one can compute that this is equal to the square root of 2 divided by 3. Hence, f2 of x is equal to the square root of 3 divided by 2 times x minus 1. Finally, the element f3 tilde is equal to x squared minus the scalar product between x squared and f1 of x times f1 of x, and then again minus the inner product between x squared and f2 of x times f2 of x. And again we can rewrite it as x squared minus the scalar product between x squared and 1 divided by the scalar product between 1 and 1 times 1 minus the scalar product between x squared and x minus 1 divided by the scalar product between x minus 1 and x minus 1 times x minus 1. So the numerators of these two fractions are not yet computed, so we need to compute them. The inner product between x squared and 1 is just the integral of x squared between 0 and 2. This is the evaluation of x cubed divided by 3 at x is equal to 2. So this is 8 divided by 3. So you'll have 8 divided by 3 here in the numerator. The numerator of the second fraction is the inner product between x squared and x minus 1. This is the integral between 0 and 2 of x squared times x minus 1 dx, which is the integral between 0 and 2 of x cubed minus x squared. And this is the evaluation at x is equal to 2 of the function x to the power 4 divided by 4 minus x to the power 3 divided by 3. And this is equal to 4 divided by 3. And now if we plug in these things in our formula here, if we plug in all computed values, we will get that f3 tilde is equal to x squared minus 4 divided by 3 minus 2 times x minus 1, which is the polynomial x squared minus 2x plus 2 divided by 3. And now this will get messy, because now the outcome f3 of x should be computed as f3 tilde divided by the length of f3 tilde. And the length of f3 tilde is the square root of the integral between 0 and 2 of this polynomial x squared minus 2x plus 2 divided by 3 squared dx. So now we can compute that the square of this polynomial is x to the power 4 minus 4x to the power 3 plus 16 divided by 3x to the power 2 minus 8 divided by 3x plus 4 divided by 9. And so the integral itself will be the evaluation at x is equal to 2 of the function x to the power 5 divided by 5 minus x to the power 4 plus 16 divided by 9x to the power 3 minus 4 divided by 3x to the power 2 plus 4 divided by 9x. And when we compute all this, the outcome will be the square root of 8 divided by 45. This means that the element f3 of x is equal to the square root of 45 divided by 8 times the polynomial x squared minus 2x plus 2 divided by 3. And the answer is that the following polynomials form an orthonormal basis in our Euclidean space. The first polynomial is 1 divided by root of 2. The second polynomial is the root of 3 divided by 2 times x minus 1. And the third polynomial is the square root of 45 divided by 8 times x squared minus 2x plus 2 divided by 3. So it's quite a messy answer. Let us now discuss some nice properties of orthonormal bases. Property 1. Let E, consisting of E1, E2, and so on, Ek, be an orthonormal basis in an Euclidean space E. Then, for any element V in E, we have that the element V, when we write it as a linear combination of the basis elements, is given by the following formula. So it's a sum over all I from 1 to k, and then we have the basis element EI with the coefficient given by the scalar product between V and EI. Proof. So we know that each element can be uniquely written as a linear combination of basis elements with some coefficients. So let's write it as a sum I from 1 to k lambda I EI. Then, for any index j between 1 and k, we can compute the scalar product between v and ej in the following way. So instead of v, we plug in this linear combination. So we have the scalar product between the sum of lambda I ei with ej. So we use the linearity of the scalar product to rewrite it as a sum over all I from 1 to k lambda I times the scalar product between ei and ej. But E was an orthonormal basis, so this scalar product is 0 unless I is equal to j, and in the latter case, the scalar product is 1. So we will get exactly lambda j. So the scalar product between V and Ej is equal to lambda j, which proves our property 1. Property 2. Again, let E be an orthonormal basis in an Euclidean space E. Then, for any two elements V and W in E, the scalar product between V and W can be computed as the sum over all I from 1 to k, and then we take the product of two factors. The first vector is the scalar product between V and EI, and the second factor is the scalar product between W and EI. Proof? Let's compute the scalar product between V and W. By property 1, we know that V is a linear combination of EI's with coefficients the scalar product between V and EI. Similarly, W is a linear combination of EJ's with coefficients the scalar product between W and EJ. Using the bilinearity of the scalar product, we can move all sums and coefficients out, and we will have this formula. The sum over all I from 1 to k, the sum over all j from 1 to k, the scalar product of V and EI times the scalar product of W and EJ times the scalar product between EI and EJ. And the last factor is equal to 0 if I and j are different, and it's equal to 1 if I and j are the same. So the whole expression is equal to the sum over all I of V scalar product with EI times W scalar product with EI, which is exactly what we want. And another way to write the same property is that if we write V as a linear combination of the basis elements with coefficients lambda I, and W as a linear combination of the basis elements with coefficients mu I, then the scalar product between V and W is just the sum of products of the corresponding coefficients. Please note that this property is about orthonormal basis in the Euclidean space. If we choose a basis which is not orthonormal, all this is not true in general. Property 3, again, let E be an orthonormal basis in an Euclidean space. Then, for any element V in E, the square of the length of V is equal to the sum over all I from 1 to k, and then the square of the scalar product between V and EI. This is a direct consequence of property 2. We just plug in W is equal to V in this formula, and we get exactly property 3. And this property can be considered as a higher dimensional generalization of the Pythagorean theorem. In the case k is equal to 2, this property reads that the length of V squared is equal to the scalar product between V and EI squared plus the scalar product between V and E2 squared. And here is a picture. So we are in the two-dimensional Euclidean space. We have the orthonormal basis E1 and E2, and we have some vector V. The scalar product between V and E1 by the first property is exactly the coefficient when we write V as a linear combination of E1 and E2. So this is exactly the length of the projection on V onto the x-axis. And similarly, the scalar product between V and E2 is the length of the projection of V onto the y-axis. And then this property says that if you look at this triangle on the picture, then the square of this side is equal to the sum of the squares of this side and this side. And the main point is that the vectors E1 and E2 are orthogonal, so this angle is 90 degrees. And we get exactly the Pythagorean theorem. Now let us talk about orthogonal complement. Let E be an Euclidean space and V be a subspace of E. The orthogonal complement of V is defined as follows. This is a notation for the orthogonal complement. The orthogonal complement consists of all vectors W in E, which are orthogonal to all elements of V. So here are some immediate properties of the orthogonal complement. Each orthogonal complement contains the zero vector, because the zero vector is orthogonal to all vectors in our Euclidean space. Second property, the orthogonal complement is a subspace. If we have two vectors w and w prime in the orthogonal complement, and we have any vector v in the original space capital V, then the scalar product between the sum of w and w prime with v, using the bilinearity of the scalar product, is equal to the sum of the scalar product between w and v and the scalar product between w prime and v. The first one is 0 because w is in the orthogonal complement. The second one is 0 because w is in the orthogonal complement. So the sum of 0 plus 0 is 0, which shows that w plus w prime belongs to the orthogonal complement. So the orthogonal complement is closed with respect to taking sums of the vectors. Furthermore, if we have a vector w in the orthogonal complement and any scalar lambda in real numbers, and any vector v in V, then the inner product between lambda w and V can be computed as follows. We can move out lambda using bilinearity, and we get lambda times the inner product between w and V. Since w is in the orthogonal complement and v is in V, this inner product is 0, so we get lambda times 0, which is 0. And this shows that lambda v belongs to the orthogonal complement. So the orthogonal complement contains a zero vector and is closed with respect to taking sum and multiplication with real scalars. This means that it is a subspace of our Euclidean space. Property 3. The intersection of V and the orthogonal complement of V consists of the zero vector. Proof? If we have any vector in this intersection, then by the definition it is orthogonal to itself. So the length of this vector is 0. But because we are in an Euclidean space, only zero vector has zero length. So V must be 0. And this completes the proof. Property 4. Every element W in E can be written as a sum of two elements x and y, where x is in V and y is in the orthogonal complement of V. Proof. As we have already seen, any Euclidean space has an orthonormal basis. So let us choose an orthonormal basis E1 and so on Ek in V. Then let us denote by x the linear combination of these elements Ei with coefficients given by the inner product between W and Ei. This, by definition, is an element in V. So what we need to prove? We need to prove that if we look at the difference between W and this element x, that this difference ends up in the orthogonal complement to V. In order to prove this, we need to prove that this vector is orthogonal to any vector in V. But using the bilinearity of the scalar product, it's enough to check that it's orthogonal to any generating system of vectors in V, and we have a generated system of vectors, our orthonormal basis. So we only need to check that W minus x is orthogonal to any Ej from our orthonormal basis E in V. Here's a computation. Let's compute the scalar product between W minus x and Ej. So we plug in the expression of x, which we used to define it, and use the bilinearity of the scalar product. So we get the scalar product between W and Ej minus the sum over all I from 1 to k, the scalar product between W and Ei times the scalar product between Ei and Ej. So this later factor is 0 if I is not equal to j, and is 1 if I is equal to j. So in this case, we will get the first summand is the same, and from this sum, only one summand survives, and then it's exactly the same summand W scalar product with Ej. So if we subtract them, we get 0. And this completes the proof. Here are some more properties. Property 5. If you take an element in E and write it in two ways, as a sum of two elements x and y, and x prime and y prime, where x and x prime are in V and y prime are in the orthogonal complement to V, then x is equal to x prime and y is equal to y prime. So the decomposition given by property 4 is unique. So the claim is that this way to write W as the sum of an element in V and an element in the orthogonal complement of V, this way to write W is unique. Proof. So if x plus y is equal to x prime plus y prime, as in the formulation of the property, so we can just move x prime to the left and here y to the right, and we get that x minus x prime is equal to y prime minus y. But x minus x prime is in V, and y prime minus y is in the orthogonal complement. And the intersection of the two is only the zero vector. So x minus x prime is the zero vector, and y prime minus y is the zero vector. And it follows that x is equal to x prime, and y is equal to y prime. Next property. So if we have an orthonormal basis in V, let's say it's a basis E1 and so on Ek, and if we have an orthonormal basis in the orthogonal complement of V, let's say that it's a basis E1 prime and so on En prime, then uniting these two bases, we get an orthonormal basis in the whole Euclidean space. In particular, the dimension of the Euclidean space is equal to the sum of the dimensions of V and of the dimension of the orthogonal complement of V. Proof. Any element in E can be uniquely written as x plus y, where x is in V and y is in V orthogonal complement. So we can write x as a linear combinations of elements E1 and so on Ek, because E1 Ek is a basis in V. And we can write y as a linear combination of E1 prime and so on En prime, because the latter is a basis in the orthogonal complement to V. And so x plus y will be a linear combination of E1 and so on Ek, E1 prime and so on En prime. And so this collection generates E. Great, so this is a generating system. Next property, we want to prove that this collection is linearly independent. So if we have a linear combination of these elements which is equal to 0, we can move the second sum to the right, and we have that the first sum is equal to the second sum, but the first sum is in V and the second sum is in the orthogonal complement, so they both should be equal to 0. And therefore, all lambda i's should be 0 because E1 and so on Ek is a basis in V. And all mu j's should be 0 because E1 prime and so on En prime is a basis in the orthogonal complement. And therefore, this collection is linearly independent, and hence it's a basis in E. Well, by definition, all elements in this collection have norm 1 because they come from an O and B in the subspaces, and they are pairwise orthogonal. So the first elements are orthogonal to each other because they come from the O and B. The second collection of elements is orthogonal to each other because they come from an O and B. And each element in the first collection is orthogonal to each element in the second collection because the first collection lives in V and the second collection lives in the orthogonal complement to V. And so this basis is an O and B. And this completes property 5. And finally, let us define the notion of an orthogonal projection. Let E be an Euclidean space and V a subspace. Then any element V in E can be uniquely written as a sum of two elements, x and y, where x is in V and y is in the orthogonal complement to V. Definition: the vector x is called the orthogonal projection of W onto V. And the notation is that x is the projection onto V of W. One can check that this map projection onto V, this is a map which starts from a vector in E and outputs a vector in V. This map is a linear map. Here is an example. So if you take the two-dimensional Euclidean space, a standard two-dimensional Euclidean space, and we take as V the linear span of the first basis element E1, then the orthogonal complement to V is a linear span of the second basis element E2 because E1 and E2 are orthogonal. And the projection onto V of the vector AB, this is a vector in E2, this is equal to the vector A in V, and the projection of the vector AB on the orthogonal complement is equal to the vector B in this orthogonal complement. Let us finish with some problems and questions. Question 1. Construct an ON beam in the set of all solutions to the linear equation x1 minus 2x2 plus x3 minus x4 is equal to 0, considered as a subspace of the standard Euclidean space E4. Question 2. Construct an ON beam in the space of all polynomials of degree at most 2 with respect to the inner product given by the integral between minus 1 and 1 f of x g of x dx. Question 3. Construct an orthonormal basis in the space of all polynomials of degree at most 1 with respect to the inner product given by the integral from 1 to 2 f of x g of x dx. Question 4. Prove with all details that the linear map, which takes an element in E and outputs its orthogonal projection onto a subspace V, is linear. And question 5. Prove that the restriction of this projection map to V coincides with the identity map. Thank you very much and see you next time.